lots of formulas that you're going to need to write down for your formula sheet. All right, so to be able to do center of mass and moments of inertia, we have to be able to define the mass of a planar lamina of variable density. So in 7.6, it was discussed that several applications of integration involving a lamina of a constant density rho can be covered. Let's say that we have some region here say from A to B. Okay. If the lamina corresponding to this region has a constant density rho, so lamina corresponding to that region has a constant density rho, then the mass of that lamina is given by rho times the double integral over the region dA. Alright, or you could just say the double integral of over the region, whatever, you have to figure out the boundaries of rho dA. Okay, so that's the formula for mass of a planar lamina that I guess is usually covered maybe in an intro physics class. Usually though, it may be just given as a single integral, which would change things up just a little bit. In this section, since we do understand double integrals, we can use double integrals to find the mass of a lamina of variable density. So usually with single integrals, we would have to have a constant density. But with double integrals, since we can integrate with respect to different variables, we can find the mass of a planar lamina of variable density. So the only difference is, instead of rho just being a constant, you actually have a function, rho of x, y, okay? So there's not a whole lot of difference. It's just that it's kind of, back in chapter 7, before we knew how to do double integrals, and we have not really explored variable or equations of 2 or 3 variables, then we really couldn't talk about anything I guess as cool as this. You'd want to think of it, maybe if you think of things in 2 dimensions and you can only do area, well then in 3 dimensions we can do volume. Well, it's the same here. When we start talking about 3 dimensions and we use multiple integrals to evaluate things in 3 dimensions, then we can do cooler stuff. Alright, so this is the main formula that I would write down, and this is how you find the mass of a planar lamina of variable density. Alright, so let's find the mass of a planar lamina. Let's do one from the back of the section. So how about number 2? Usually starting with the smaller numbers it's pretty good. The directions say, and I can copy this down for you. I'm not going to use this online other than to give it to those students who are working. I don't have to worry about copyright infringement or anything. Alright, so finding the mass of a lamina. So we're given in the directions what the density of the planar lamina. It does right here say some of the integrals are simpler in polar coordinates. Not that you can't do them in rectangular coordinates, it's just if you change it to polar coordinates it'd actually be easier. So how about we try number 2? Okay, so we know we're going to have the double integral. Find the mass of the planar lamina. It's going to be the double integral over the region, and so it depends on how we set up our dA, if we decide to do dy dx, or if we decide to do r dr d theta if we change it to polar. So it really depends on what we decide to use as our differentials as to how we set it up. But your row of xy is just xy, and then dA. So since we have x and y, it's probably going to be easiest just to set this thing up. Look, you have a variable with your y, like you have your y defined and you have a variable here, and you have your x defined with just constants. So it would make the most sense to set this thing up dy dx, because remember we always want to have constants out here on the furthest integral if we can. And so this inside integral here, this is going to be from 0 to 9 minus x squared. Okay, so we want to integrate with respect to y first. So I have the integral from 0 to 3, and that's going to be x y squared over 2. I'm going to evaluate that from 0 to 9 minus x squared. Now remember, whenever we had to integrate and hold x as a constant, but whenever you go to evaluate, you plug in for whatever variable you just integrated. Alright, so I want to plug that in for y. If you want, you could go ahead and move that 1/2 to the outside. You can just leave it in there too. That's fine. Alright, so this is going to be the integral from, and I forgot my differential, don't be bad like me. The integral from 0 to 3 of x times, if I plug in that, my top boundary, that's just going to be 9 minus x squared, and I chose to just write it like this because when you plug in the bottom boundary you get a 0, and so 0 is not going to make a difference. Alright, now to integrate that though, I mean, either you multiply it out and integrate it, or you see that if what's in the parentheses is your u, then you do have that x to the first on the outside, right? So either you square that and multiply times x, write all that as one big long polynomial and integrate, or you say, well, if I let u equal 9 minus x squared, then du is negative 2x, and I have the x on the outside, so I just need to bring out a negative 1/2. And then it's the integral of u squared. Right, so if I bring out a negative 1/2, I'm going to have negative 1/4 u squared. Now that's not the answer. I mean, that's just how we rewrite it if we want to make that my u, right? So integrate that, and that's going to be, and that's not dx, it's actually du now. But integrate that, and that's going to be negative 1/12 u to the what? Third, right? Because it's u to the third over 3. That's 1/12. And you have to evaluate that from 0 to 3. Now, before you evaluate, though, don't do like I've done in the past. Just like if I'm working problems for fun on the weekends, don't just plug these numbers in. Remember, you got to plug your u back in. I've done that before, and it makes me feel really bad whenever I do that. So I let my u be 9 minus x squared. So it's negative 1/12 times 9 minus x squared cubed. Alright, and then that's what I want to evaluate from 0 to 3. This is one of those times when plugging in 0 doesn't give you 0, so be careful there. I have negative 1/12. That's a constant, so I'm just going to leave that on the outside, and then I'm going to do my work in here. Now, when I plug in a 3, I get what? 0 minus, now when I plug in a 0, I get 9 to the third power. 9 times 9 is 81 times, wait, is that right? Yeah, I think so. 9 times 9 is 81 times 9 is that 729? Alright, so when I plug in a 0, I get 729. So I have negative 1/12 times negative 729. So that's going to be a positive 729 over 12 units. Let's see. I think you can divide both of those by 3. $243. Now, if I was to work that out and get a negative answer, remember this is mass. So I'm not going to get a negative answer. So this is my mass of the planar lamina. All right. Are there any questions on mass? Now we have to use the mass in order to do some of the stuff that we're, in the second half of the section. But first we need to be able to find the mass. So how about I go to the next section of problems. All right, the next section of problems is dealing with the center of mass. So to find the center of mass, I do have to be able to find the mass. So before we work one of those, how about we talk about the center of mass a little bit. So, physics people, engineers, what is the center of mass? I'm not going to bring it up on Google. There's no telling what it would come up if I did that. What's the center of mass? Think about it. Now, you probably don't want to say the same thing. It's one of those things that may be kind of tough to explain. I guess it'd have to be balanced, right? Everything just right there in the middle. I wonder what the official definition is. I just hate to. Maybe if I go to Wolfram Alpha may have a better explanation of it. Let's see. See what it says. Point representing the mean position of the matter in a body. Okay. So there's only one point. That's the center of mass, and it's some xy. Okay. So if we have some planar lamina here, you can see the center of mass is some point, some actual point there. See what your book says. For a lamina of variable density, moments of mass are defined in a manner similar to that used for the uniform density case. For a partition delta of a lamina corresponding to a plane region R, consider the ith rectangle R sub I of one area delta A sub I as shown in figure 14.36. Assume that the mass of R sub I is concentrated at one point of its interior points, X sub I, Y sub I. The moments of mass of R sub I with respect to the x-axis can be approximated by saying the mass times Y sub I. Similarly, the moment of mass with respect to the y-axis can be approximated by saying the mass times x sub I. By forming the Riemann sum of all such products and taking limits as the norms of delta approach 0, so that's just making all of those rectangles, their widths are approaching 0, you obtain the following definitions of moments of mass with respect to the x and y axis. So, to figure out the moment of mass with respect to the x, it's the double integral over the region R, of y times the variable density here, dA. So whenever you want to find the moment with respect to the x, you have to put a y in front. And then you can see here the moment with respect to the y, you have to put an x in front. Okay? Once you calculate those two, then you also have to calculate the mass. So you could do that first, and then calculate the moment about the x and the moment about the y, or the moments with respect to the x, moments with respect to the y. Because you have to say the moment with respect to the y divided by the mass to get the x, or x bar here in the center of mass. And you have to say the moment with respect to the x divided by the mass to find the y coordinate. Alright, another name for, it says if R represents a simple plane region rather than a lamina, then the point x bar, y bar is called the centroid of the region. Alright, so you need to find the mass, you need to find the moment about the x-axis, moment about the y-axis, and then you can't, make sure you have this formula written down. For the x-coordinates, the moment about the y divided by the mass, and for the y-coordinates, the moment about the x divided by the mass. Alright. So let's see if I can find a problem. Got a lot of good problems here in your book. Alright, so it doesn't matter which one we really do. I'm going to pick 16. Notice that row, that the density here has k times y, k times xy. Is different, of course, but what is k going to be understood to be? A constant. Okay. So just let k go along for the ride. I mean, it's a constant, so it just goes along with whatever we do. Okay. So let's see. For number 16, we need to figure out the mass. Then we need to figure out the moment about the x-axis, the moment about the y-axis. Alright, so see if you can set up the equation that would give us the mass. So this is like we did on the previous problem. Alright, so it's going to be the double integral. Alright, so we got a lot of different equations here. Let's see. We might want to just do like a really rough sketch of what's going on. You see we have the line y equals 0. We also have the line x equals 0. We also have the line x equals 1. So let's just say this is x equals 1. Y equals e to the negative x. So this let's see. So if this is 1 on the y, then this graph, what's it going to do? So if x is 0, y is 1. Let me make it a different color. Because 0, y is 1. When x starts to get larger, this starts to get smaller and approach 0. Right? So this does, I believe, go out like that, and see, like when x is 1, that's going to be 1 divided by e to the first power. So that's it's already going to be getting small, and this just continues to go out and out forever. Okay, so I guess we're talking about this region right here. Alright, and so that's what we're trying to figure out the mass of. So what is our formula for mass going to be? Well, what is this right here? That's the easy part. What are we integrating? And what's so it's k y squared. Now probably dy dx. Looks like we can bound the x pretty easy. Right? How do we bound the x? 0 to 1. So yeah, that one's pretty easy. Now the y is going to be from 0 to this line right here. So 0 to, what was this that we graphed? E to the negative x. So it's not as complicated as you would think. I mean, once you write it down, you may get a little confused at first, but we're basically setting up these the same way we've set up anything else. All right, so we want to integrate with respect to y. Well, that's pretty easy. Integral 0 to 1 k y cubed over 3. And then we want to plug this in for y. Alright, so we're going to plug in e to the negative x. Right? And then you're going to say minus plug in 0. But I think you can tell what happens when you plug in 0 there. Right? When you plug in 0, you get 0. So then we're just going to have, what happens when you plug this in? What are you going to get? E to the negative 3x, because it's e to the negative x cubed, multiply the powers. Alright. Dx. Remember, plugging in the 0 gives you 0, so you don't have to worry about that. Alright, so that's going to equal, now integrate with respect to x. Remember, when you integrate, all of this is a constant. When you integrate e to the negative 3x, your u is negative 3x, so your du is negative 3, so you got to bring out a negative 1/3. Alright, so it's going to be negative 1/3 k over 3, that's a constant, e to the negative 3x, evaluated from 0 to 1. Now, be careful here, because plugging in a 0 does not give us 0. Okay? Right, because it's that's a power of e. Right. So I have negative 1/9. I could really just write that as negative k over 9. And now let's deal with this, because all that's a constant. So if I plug in a 1, what do I have? E to the negative 3 power. And then minus, if I plug in a 0, what do I have? 1. Now, if I had to guess, since remember, this mass is going to be positive, the best way of writing this answer would be to factor a negative out of this, so that you would have 1/9, a positive 1/9 on the outside, times 1 minus e to the negative 3 times k. Usually that's how it would be written. your final answer. It's kind of like that k, that constant there is usually written at the end. Okay. Now, if you would have left it like this, it would not have been wrong. But I'm just telling you, if you were to look this up in the book, or you know, it's probably going to be written like that. Just to get rid of that negative there. Alright, so that's the mass. So now we need to figure out the moment about the x and the moment about the y-axis. The moment about the x, we'll do that one first. Remember, we pretty much use the same formula. The only difference is that whenever you take the moment about the x, you put a y in front of your density function. So as far as the way we set everything up, it's all going to be the same, except we're going to have a y in front of my density function, which, yes, makes that y what? Cubed. So it's going to be ky cubed dy dx. All of our boundaries are going to stay the same because it's the same figure. I mean, we didn't really change anything. Alright, so I mean, you can probably work through this integral a lot faster once you've already worked through the other one. So it's going to be y to the 4th over 4. We just have to evaluate that. Okay, so that's going to be e to the negative 4x dx. So then that's going to be where your du here is a negative 4, so you bring out a negative 1/4, so that's negative k over 16 e to the negative 4x evaluated from 0 to 1. Okay, so that's going to be negative k over 16 times e to the negative 4 minus e to the 0, or minus 1. Again, you'd probably want to factor a negative out of here and write this as 1/16 times 1 minus e to the negative 4th times k. It wouldn't be wrong the other way, it's just that typically that's the way it would be written. Alright, so that's the moment about the x axis. Now we need to figure out, and you might want to make sure you label everything as good as you can, because you are going to have a lot of work here. And so the moment about the y, that's going to be, the only difference here, we're doing the same integrals except you put an x in front of the density function. Now that you know, doesn't really change much here. Dx, all the same boundaries. It looks like that's going to change one of my integrals, though. Not going to change my first integral really that much. Still a power rule. That's going to be all that over 3, evaluated from 0 to e to the negative x. So that's going to be e to the negative 3x You see why I say it's going to change this next integral? Because you have an x in front. So I'd kind of probably think about it like this. Move your k over 3 out front. We have the integral of x e to the negative 3x dx. That is a integration by parts. Okay. So let's see what that would be. So u and dv, let u equal x, let dv equal e to the negative 3x. So du equals 1, so v equals negative 1/3 e to the negative 3x. So this integral is k over 3 times u v, so it's negative 1/3 x e to the negative 3x minus the integral of v times du. And then whenever you do all of that, once we do this other integral, we're going to evaluate everything from 0 to 1. Okay, hopefully I haven't missed any signs or anything. We'll see in a second. Alright, I do see two minuses right here, so I'm just going to go ahead and make that a plus. But then I have to bring out a negative 1/3. So that's going to be minus. If I bring the 1/3 out and bring out a negative 1/3, that's minus 1/9 e to the negative 3x. And don't forget that we need to evaluate that from 0 to 1. Now, since I did integrate with respect to x there, I'm plugging this in for every x. So plugging in a 1 for this x, I get negative 1/3, and then that's a 1 e to the negative 3. And then I plug in the 1 again here, that's minus 1/9 e to the negative 3. So that's what I get when I plug in a 1. Minus, when I plug in a 0, this first term is going to go away because of that 0. This second term is going to be minus 1/9, and then that's going to be e to the 0, so that's going to be times 1. Alright, so let's see if we can simplify this little monster here. Alright, so minus a negative, so that'll be plus. Looks like we have a constant of 1/9 there. Probably, if I had to guess, we're going to be able to factor a 1/9 out. Alright, but you know, these are like terms. No matter how crazy they look, this here and this here are like terms. This is negative 1/3 of these, and this is negative 1/9 of these. So you can really think about the e to the negative 3 like it's a variable. Just like whenever you're dealing with radians, you can think about pi like it's a variable. Because we're saying negative 1/3 of these and negative 1/9 of these. So this is 9th. If you put that in ninths, that's negative 3/9, and that's negative 1/9. So that's going to be negative 4/9 e to the negative 3 plus 1/9. Now to make this thing a little prettier, did I miss a negative sign somewhere? That's what I need to make sure that I didn't miss a negative sign. I guess it all looks, no, I didn't miss a negative sign. Everything looks good. To make this prettier though, since I noticed that this is a ninth and this is a ninth, you may want to, first of all, write the constant first since it's positive here, and this second, but factor a 1/9 out. You may say, why would I want to factor a 1/9 out? You don't have to, but it makes the answer look a little prettier. If you factor a 1/9 out, that would be k over 27. And then in here, and I'm going to rewrite it, but you'd have -4e to the -3 plus 1. I'm going to rearrange these terms. I'm also going to write my k at the end. So if you were to look this answer up in a textbook, the most simplified form of this answer would be 1 over 27 times 1 minus 4e to the -3 times k. Alright, so we're almost done. Now we just need to figure out our mean x and mean y. So x bar and y bar. So x bar is the moment about the y divided by the mass. So we just figured out the moment about the y axis. That was this integral. So that's 1 over 27 times 1 minus 4e to the -3 times k divided by the mass, which was what we figured out first. The mass here is 1/9 times 1 minus e to the -3 times k. Alright, you'll see there's some things here that are going to cancel out. You know, you have a fraction over a fraction, so of course, since I'm multiplying here, you can just flip and multiply that. Also, the k's cancel out. Okay? The k's cancel out, okay? So that's going to be, when you flip and multiply, that's going to be 9 over 27. So that's what? 1/3 times 1 minus 4e to the -3 over 1 minus e to the -3. You could just write this as, since this is a 1 here, you could just write this as 1 minus 4e to the -3 over 3 times 1 minus e to the -3. That's a number, right? Because we know e has an approximation, but you'd want to leave your answer like that. So that's x bar. That's our x coordinate. And now y bar is the moment about the x divided by the mass. So that was, where's the moment about the x? Up here, 1/16 times 1 minus e to the negative, was it -3? -4. -4. -4 times k divided by that same mass. The k's cancel out. Whenever you simplify that, you end up getting 9 times 1 minus e to the -4 over 16 times 1 minus e to the -3. And so your center of mass is x bar, y bar. So it's this as the x, this as the y. So really, we're done for the day. We didn't get a chance to get into the last part.